So, hello everyone. Today I am going to start the first lecture of week 2, that is metabolic, stoichiometric and energetics. So, the learning out goals for today's lecture will be material balance, how we apply the conservation of mass, what are its implications particularly in bioprocess industries or bioprocess engineering. So, if you go ahead, does it mean is mass is conserved at all times in biological processing, and this is also true for bioprocess. So, as we know this in bioprocess there are metabolic pathways that are exploited to synthesize the desired metabolites, but here this material and mass balance is looking at macroscopic level. So, as the name suggests, balance means what we are balancing is the mass which is entering or leaving the system. So, in the bioprocess, what is the system? Typically the system is, in the bioprocess typically the system is bioreactor or fermenter. And here some mass is coming and some mass is out. So, we have to balance between these two, that is called the balance. So, what I was telling, if you see the any biological system, so there will be n number of streams which are going in, and similarly there will be n number of streams which are going out, and practically it is not feasible to measure the mass and composition of all the streams. So, what happens when we do the mass balance? So, that enables us to calculate the mass and composition of most of the streams, which is difficult to experimentally measure. So, how it is done? It applies the law of conservation of mass. So, basically it provides the theoretical framework for material balance. So, the objective is we should be able to get the unknown quantities using this mass balance principles. So, for example, in a typical bioprocess we are going to add the substrate, and if it is aerobic we are going to supply the air. Now, in the flue gas or in the off gas there will be carbon dioxide and other gases, and in addition to main product or metabolite there may be formation of other byproducts. So, typically it is not possible to have the sensor or detect and quantify all the inlet and outlet streams. So, if you can apply the mass balance, we should be able to calculate what is the fermentation efficiency, means how much the substrate is being converted to your desired product, how much it is accountable for other byproducts, and at the same time, as you know, in the bioprocess cells are also considered to be product. So, how much substrate is going to the biomass. So, mass balance theme, it gives the mass of some input and output and calculate the mass of others. So, basically when you are going to balance this mass, so we will have some unknown masses and some known masses, and the whole idea is to calculate the unknown amounts or unknown mass. So, what are the implications? For example, as I discussed, what we should be able to calculate. So, one should be able to calculate that fraction of substrate going to the product. As I told, there may be some formation of off gases. So, you should be able to quantify the formation of off gases. For example, carbon dioxide. This also helps to quantify how much, if it is aerobic process, let us say if it is aerobic process, then it tells that amount of oxygen required. amount of oxygen required, that is considered as the inlet parameter. Typically for the oxygen we do not supply the oxygen, rather we supply the air in the bioprocess. So, these are the few questions which you should be able to answer if you apply this material and mass balance. So, first I will summarize the law of conservation of mass, then we will see how it can be applied in bioprocess. So, if you consider this is a system, as I told in the bioprocess, the system is your bioreactor or fermenter, and there is a inlet stream, outlet stream. There can be n number of inlet streams and n number of outlet streams. So, the when we apply this law of conservation of mass, so it says mass, total mass in minus total mass out plus generation minus consumption, that should be equals to the accumulation. So, this is the general equation of mass balance, or you can say general material balance equation. Now, this equation is applied for the biomass, this also apply to the substrate, and this also apply to the product. So, let us say for example, in the case of if I apply this equation for substrate, there will be no generation. So, this term will be 0 and there will be consumption. So, this term will be there for the substrate, but at the same time when I go for biomass, then there will be no consumption of biomass, rather there should be generation term of biomass. Now, next comes this accumulation. This accumulation can be both positive or negative. As I told, if you are doing the mass balance for biomass, the accumulation will be positive. If I am even doing this mass balance for the product, accumulation will be positive, but when I am doing this mass balance for the substrate, the accumulation will be negative. So, when we apply this general mass balance equation, now we can have three different processes in bioprocess engineering. We start with the batch, fed batch and continuous. So, why I am discussing briefly here is to understand this inlet and outlet. So, in the batch, as you see, there is no inlet and no outlet streams. In the fed batch, there is a only inlet stream, there is no outlet stream, and in the continuous both inlet outlet streams are there. So, when we are going to do this mass balance, so in the case of continuous, what we take? We take the rate of mass in and rate of mass out. So, this balance is called differential balance. While we in the case of batch and fed batch, at the end of process we do the mass balance based on the total quantity, and when you are doing based on quantity in the place of rate, so that is called integral balance. So, mass balance, when we are doing mass balance using rate, that is called differential balance. When you are doing mass balance using quantity in place of rate, that is called integral balance. Now, there is one term called steady state. Steady state means the rate of inlet and outlet is same. So, it says accumulation term is also 0. So, in the mass balance equation, that was in minus out plus generation minus consumption equals to 0, because accumulation term is 0, and if you just rearrange it, so this will be in plus generation equals to the out plus consumption, and this modified equation is called general steady state material balance equation, because here the accumulation term is 0. So, now you can correlate here This for the batch and the fed batch, we are going to apply general material balance equation, but for the continuous you have to apply general steady state material balance equation. So, to understand that how this material balance looks like, we will briefly discuss one example. So, it says acetobacteria converts ethanol to acetic acid. So, here ethanol is your substrate and acetic acid is your product. Under aerobic condition, aerobic means it also require the supply of oxygen. And which type of process is there? This is a continuous fermentation process. For vinegar production is proposed using non-growing acetobacter cells immobilized on the surface of gelatin bits. Now, how air is supplied? How oxygen is supplied? Through air is pumped into fermenter at the rate of 200 gram mole per hour. So, the flow rate of, or you can say the inlet rate of air is given over here, and the production target is 2 kg per hour for the acetic acid, and at the same time the maximum concentration of acetic acid should be 12%. Now, to understand this, what we have to do? We have to draw a flow diagram of the process clearly depicting what are the inlet and outlet streams. Then we have to apply the law of conservation of mass, and followed by that we have to calculate first what is the minimum amount of ethanol required, what minimum amount of water must be used to dilute ethanol to avoid acid inhibition, and what is the composition of fermenter of gas. So, now we just see what are the information given to us. This air flow rate is known and product formation rate is known, and these are the unknowns. So, these unknowns can be calculated using the principle of conservation of mass. So, as it says, so first what we have to do? We have to go for a first step to draw the flow diagram. This is your fermenter. Inlet, what is inlet? Is the feed. Let us say it has E kg per hour of ethanol. At the same time, it will also have W kg per hour of water. What is your product? Your product stream is P kg per hour of acetic acid, and that is given as 2 kg per hour or 12%. In addition, this air is entering and there will be generation of off gas. Now, typically air contains both oxygen as well as nitrogen. So, what will happen? Oxygen will be utilized in the reaction, but nitrogen will directly go into the off gas. Now, what is the air flow rate? Is given as, it is 200 mole per hour. How much air is supplied? 200 mole per hour. Now, as we know, the air it contains 21% typically oxygen and 79% nitrogen. So, we can calculate what is oxygen and how much nitrogen is being supplied. So, if I do this 21%, so this will be 21 into 200 gram per mole into mass of oxygen is 32. So, we are going to get oxygen will be 200 into 0.21 into 32. So, this will be equals to 1344 gram or 1.344 kg. Now, same if I do for the nitrogen. So, nitrogen is 0.79 into 200 and its molecular weight is 28. We are going to have 4424 gram or 4.424 kg. So, as I told, nitrogen will directly go out, it will not participate in the reaction being inert. 4.424 kg it directly goes out. Now, in the product we are having 2 kg per hour or 12% weight by volume. Now, the first thing for the material balance or mass balance is to have the flow diagram that we did it. Now, next requires how the substrate is converted to the product. It means we need to have that equation which is converting the substrate to product. So, that we will be writing here, that is C2H5OH plus oxygen, and this will convert to acetic acid CH3COOH plus H2O water. Now, it says the 1 mole of ethanol is converted to 1 mole of acetic acid, it requires 1 mole of oxygen and 1 mole of water will be also produced. Now, considering this, we already know what is the molecular weight of ethanol. The ethanol molecular weight is 46, oxygen is 32, acetic acid 60 and H2O is 18. Now, here let us assume assume T equals 1 hour. So, how much acetic acid is formed? 2 kg. In 1 hour, how much acetic acid will be formed? Is 2 kg. And if I convert this acetic acid into moles, then you have to have this 2000 divided by 60, and this equals to the 33.33 mole or 3.333 into 10 to the power minus 2 kilomole. So, how much ethanol is consumed here? How much ethanol is consumed? For 1 mole, this requires 1 mole. So, for 3.333 10 to the power minus 2 kilomole. So, this much moles of ethanol has been consumed. So, that is 3.333 into 10 to the power minus 2 moles. Same for oxygen also, 3.333 into 10 to the power minus 2 moles has been utilized, and how much water is formed is 3.333 into 10 to the power minus 2 kilomole. Now, we can directly convert this mole into mass. So, for ethanol we know its molecular weight 46, we multiply, so we will get mass 1.533 kg of ethanol is consumed. What about oxygen? Multiply with 32, we will get 1.067 kg of oxygen consumed, and how much water is generated? You multiply with 18, you will get 0.600 kg of water is being produced. Now, interestingly, in acetic acid, what it says is it should be 12% volume by volume. It means in the acetic acid 88% H2O is already present. How much water is there is 88% water and 12% is acetic acid. Acetic acid. So, now we know the acetic acid is 2 kg. So, total product stream will be 2 upon 0.12, that is equals to 16.67 kg is the total mass of outlet, and out of 16.672 is the acetic acid. So, water will be 14.67 kg. So, now if I redraw the same picture again here. So, what we have calculated so far is we are supplying this oxygen. How much oxygen we have supplied is 3. We have supplied is 1.344 kg. We have supplied nitrogen 4.424 kg. C is the off gas. In the product stream, we have acetic acid, that is 2 kg. Water is 14.67 kg. And how much ethanol was consumed? Ethanol was consumed was 1.533 kg. And how much oxygen is consumed? Oxygen was 1.067 kg oxygen was consumed. So, how much oxygen is left? Oxygen left in off gas 1.344 minus 1.067. So, that is equals to 0.277 kg. So, in the off gas we have oxygen as 0.277 kg, and as nitrogen is not participating, the whole amount of nitrogen will be in off gas 4.424 kg. Now, next comes that water. We know the water, how much water is there in the output. Let us do a simple exercise, water balance. What is the inlet of water? Let us say W, plus how much water is generated. If you remember in the last slide, water generated is 0.6 kg, 0.6. What is the water in the outlet? Water outlet is 14.67. Now, what will be the value of W? If you do the mass balance, W will be 14.07 kg. So, this much amount of water is 14.07 kg. this much amount of water is being supplied. So, what now we can go back to the question. The first part was, what is the minimum amount of ethanol required? The answer for this will be 1.5 kg per hour, because we have assumed time is equal to 1 hour. Second is, what is the amount of water must be used to dilute the ethanol? We got water as 14 kg per hour. And what is the composition of fermenter off gas? So, fermenter off gas we got 0.277 kg of oxygen, and nitrogen is unutilized 4.424 kg of nitrogen, and this equals to the 8.656 into 10 to the power minus 3 kilomole. So, this becomes 0.1580 kilomole. So, typically off gas is reported in terms of what is the percentage of nitrogen and what is the percentage of oxygen. So, if you take the total off gas, this will be equals to 0.1667 kilomole. So, we can calculate oxygen, this will be 5.19%, and nitrogen, this will be raised 94.8%. So, this is the answer. So, what it says is, in the overall material and mass balance, we have to first draw a flow diagram, and we have to also write the reaction. And once these are there, then we have to make the clear assumptions that the substrate is being utilized only for product, or it is also utilized for the biomass or the formation of any bioproduct. And third thing, you have to check whether this is a steady state or unsteady state. So, I think this gave the clear idea of overview, you can say, that how material balance look like and what is its utility in the bioprocess engineering. So, in the next slide we are going to discuss the stoichiometry balance for the biomass and product formation. Thank you so much.